Hello everybody, so today we're going to be talking about a little project I've been working on for about a year and 3 months, and it's a C to SPIR-V compiler, so you can use C as a shading programming language on the GPU. So here is a little bit of what it looks like, and on the left hand side you'll see that there's a bunch of structures and there's a vertex shader, then on the right hand side there's a structure and a pixel shader. So on the left here you'll see there's a vertex structure and it has a position and a color. And then we have a bundle constant structure here. So this is the thing that you will pass from the CPU to the GPU and it will come directly into the shader. And this thing here contains some vertices or a vertex buffer, and it also contains a constant, which is a color tint. And then there's a rasterizer state structure here, which is the thing that gets passed from the vertex shader to the pixel shader, and you can use it to like interpolate state between the vertices to the pixel. But you can also use it to not interpolate the fields as well. So as you see, there's a color here that gets interpolated, but again, there is a no interpolate as well. So you'll see here with the vertex shader, it's got a little vertex keyword, and there's 4 parameters. There's the system values in and system values out. System values are like they are on HLSL, and then there's like in GLSL they're like these things you have to define in the global space. But essentially, there's a vertex index and there's like an instance index that you can pull from the SV input, and there's a system value output, and that's like the thing like the position that you set at the end of a vertex shader, and these are specifically for the vertex ones, and there's some for different, and there's system values for pixel shaders and compute shaders as well. And you'll see that the bundle constants just gets passed in via a pointer, and you can use this here. So as you see, I'm accessing the vertex buffer, and I'm pulling out the vertex structure that we have to find up here. So you'll see that you can share these structures between the CPU and GPU, and they can just be used like so. And you'll see I'm using the vertex here, and then I'm also using the color here, and I'm multiplying the color via the I'm multiplying it via the tint that's passed in via the bundle constants. Then I'm setting the state out, and this will get passed into the pixel shader calls later. So if we go over to the pixel shader on the right, you'll see there's a pixel structure, and each field in here refers to a render target. So there's only one render target right now, but you can define multiple render targets as well. And you'll see there's system values for the pixel shader. So there's some input, there's some output system values, and also the bundle constants gets passed into here as well. And with the bundle constant, this type can actually be different, and that's controlled purely by the CPU as well. You can just use a different type here and upload a different constant for the pixel shader than you do the vertex shader, which is nice. And as you see, the rasterizer state just comes in as an input variable here, and we use it here to get the color, and we store it out in the final using the final pointer, which is the pixel color there. So how does HCC compile to SPIR-V? So what it does, it's just a regular C compiler. Well, it's kind of got some restrictions, but it's mostly a regular C compiler internally. And instead of outputting to some CPU like target, it outputs to SPIR-V targeting Vulkan, the Vulkan API. And this is a binary format, so you can load it directly into the Vulkan API and start using it. There's also experimental support to use SPIR-V cross at the end of the compilation, and this is built into the compiler, but equally you can invoke this outside of the compiler as well, using the binaries that are produced from HCC. And you can target towards HLSL for DirectX 12 and also MSL for the Metal graphics API. So again, this is experimental, and I haven't actually tested this myself, but if anyone is wanting to use this, please try and submit some issues, and we'll try and get these things fixed if there's anything. And if there's any sort of suggestions or things you want to help improve, by all means, please reach out, and we can work together on that. But in future, when I plan on actually targeting these platforms myself, I do plan on doing a more direct output, a bit like how HCC compiles to SPIR-V here. It's going to be more direct, but HLSL compiles, like you'd have to take this HLSL and use like the DXC compiler to compile it to to the DirectX interpreted language, DXIL. And we plan on in the future, at least, to make HTC compile directly to that binary format, right? But unfortunately for the Metal side of things, I'm pretty sure there's not a binary format. But yeah, with Metal, we'll probably just compile directly to MSL rather than having this intermediate step here. But for now, this will do. But if anyone wants to reach out and help on any of it, right, including the direct translation to any of these things or this SPIR-V cross thing here, yeah, please reach out, because the help would be appreciated, and then we can speed this side of things up. Right, so let's talk a little bit how using C as a shading language can also help make like just writing GPU code and like triggering it from the CPU just far more simple than the current things out there. So here's a Voxel model structure. You'll notice it's got a position, it's got a half size, and it's got a color. So the color is a resource, and it's a 3D texture resource, and these are two vector 3s here. So something to take note is the vectors use scalar block alignment, meaning they are everything's aligned to their scalar, so it's a 32-bit integer, so it's 4-byte aligned. And then also another thing to take note is a resource is just a 32-bit integer underneath. So we'll go into a little bit more what that means on as time goes on. But so this means that your structure has the same padding and alignment that it does on the CPU as it does the GPU. So you won't have to worry about, you know, the standard 430, standard 140 thing and this padding that you might have done in the past. So with this, that all goes out the window, which is great. And you can just use the same structure representation, CPU and GPU, and you literally don't have to worry about anything. And then you'll notice that this voxel model is actually a buffer, right? So this other structure here, which is the bundle constants, which is passed into a compute shader. And this is used as part of the type of the buffer. So it's a read-only buffer of models. So we have an array of models for the voxel ray tracer to render, and there's an output texture here, so it's a read-write texture 2D. And this is what we'll output in the compute shader. Then there's a time variable, there's a screen width and screen height. And again, you can set both of these structures on the CPU and just pull them out on the GPU, and it just works. So here is how that code looks like in a compute shader. So you'll see there's a bundle constant that gets passed in as a second parameter here. And you can just pull the screen width and screen height out just as if it was like a regular, you know, structure. And you can also see here with the bundle constants, we pull out the model, and we use an array access here to access the voxel model. We can use the voxel model here. And then here's the CPU side where we actually set up the buffer. So you see here we map our buffer, and then we get the model, points to the models. And so for the first model, we set the position, half size, and color. And then again, that's just read from the GPU the same sort of way, right? So that's super nice. There's no hacking macros involved to get any of this to work. It's just all using the same sort of C code, which is very nice to see. So another thing that I always found a bit weird is shading languages, or some of them at least, don't have support for enums, and use enums a lot on the CPU. I use them so much, and like you just want to like be able to use them on the GPU. I know like typically you want to avoid like branching and things like this and on the GPU, but they're just really handy for many different reasons. And you know, C's had them since forever really, and it's just been so bizarre. So yeah, being able to declare an enum that's usable on the CPU and GPU, and then also declare like a lookup table, so I can convert this into a color if I wanted to. And this lookup table can just be compiled into the CPU binary and the GPU binary. And there's no problem with that. We could just share the code, and it just works. And you'll notice here there's a C99 array designated initializers, meaning what you can, you know, it all just everything's in the right slot, and you can change these around, and it will just, they'll never go out of order in that. So there's no hacking macros again, it's just C code. It's awesome. So functions as well, right? You can declare functions that you want to share across CPU and GPU. So you notice here it's an AABB versus Ray 3D, which we use in the Voxel Ray Tracer example on the GitHub page. And this can just be used on the CPU, right? Because you definitely want to do these on the CPU sometimes. And you also want to do this on the GPU sometimes, right? So having the ability to just put that in a shared compilation unit, compile it in both CPU targets and GPU targets, same code, no hacky macros, done. We also support C11. Well, we try to aim to support C11 as much as possible, and including in C11, there's a feature called underscore generic, and this is how you do generics in C. It's like an explicit function overloading in a way. So this is how you sort of declare one of those things, and it compiles in Clang, compiles in HCC, and you can use the lerp function as you can use it on on vector types as well as scalar types. And so, you don't have to use this. So if you prefer the suffixes, you've got these, but for people who prefer like an overloading for mass functions, you also get this here. So we use the G suffix to make it apparent that it is a generic, but again, you can use the explicit ones if you fancy. So another great thing about using C and not using two different languages is the fact that there's shared semantics, meaning that, we have like the the C structure initializers, right? And these structure initializers, like if you want to do this across both languages, it's not really possible to do it in this way where we sort of set the position in this sort of syntactic way. So if you want to make this work across multiple languages, you might have to sort of repeat this word model here and not have these scope things. But at least we know they'll compile basically into the same sorts of things, and the semantics will work the same. So this also means when you use the array designated initializers as well, this will just work. You don't have to refactor your code to say, we can't use these things and they have to be in the exact order, for instance, which would have to do if you use another language, maybe like HLSL, right? And if you see here as well, even for the expressions, when you do the maths expressions, you'll notice that the casting and that all works, it all behaves the same because it follows the C standard. So here there's this type called, there's an unsigned 16-bit integer called t, is set to 15. And when we do t times -1 plus 0.5f, right, it actually turns into this code down here below. And to make this behavior work across different compilers, you'd have to be a little bit more explicit, or be, because these things might work slightly differently. All these different expressions, all the semantics and everything underneath just might work a bit differently. And just having the same behavior across multiple multiple targets just is a real big help. So just to explain a little bit how this thing works, in C, if you have an expression like this, like a binary expression, what happens is t will be promoted to an integer because it's less than an int, so it gets promoted to an int. But also, because the right-hand side is an integer type and it's bigger than the one on the left-hand side, it also should get promoted to an int as well, the same type. And then because we're adding 0.5, it also implicitly gets casted to a float. So just to have the same sort of rules across that is a big help. So we also have these things that get uploaded from the CPU to the GPU known as bundle constants, and this is the primary way that they get passed up. So here's the structure on the left where we've got the two resources, and then we also have the constants as well, all in the same buffer, right? Resources and constants can go in the same buffer, because underneath secretly, these resources are technically just little constants that get passed up. So on the CPU side, this is what it looks like, right? We just got a bundle constants pointer. We're just going to set some buffer IDs, texture IDs in there, right? They're just indices. And then we're just going to set the constants in there as well. Call a function like vk command push constants, and that records it into the command buffer, records the bundle constants in there. You have to specify the shader stages. So this one is set for the vertex and fragment or pixel shader stage. So they can be different. You can set all different ones, or you can just say compute shader as well. This one is a compute shader down here, so really you'd use compute bit, but anyway. And then here's the voxel ray tracer bundle constants being passed in here, and you can just pull the data out and start using it, which is super nice. These things are limited to about, see on Vulkan you got around a limit of about 128 bytes, but I defaulted to 64 bytes in the compiler, but this number can change depending on the hardware you target, and also you can just tell the compiler to say, hey, for all these bundled constants that get compiled, make sure that they don't go over this restriction that we use in our graphics API. So you can change it all over the place. Even like 256 it can go up to for some GPUs. So it all depends on the hardware you want to target, really. So there's another thing to take note. Easy binary resources. So again, resources are just 32-bit integer handles or indices. And essentially these will do like an array lookup and then grab the actual descriptor from the descriptor set. And it will only do this once. So I wouldn't worry about there being like, oh, but you're indexing every time I use this resource in the GPU, because it will optimize out into one array lookup and then it'll just be using that same descriptor from then on out. So if you see here, these are CPU and GPU visible structures. So there's the ray tracer bundle constants and there's the voxel model. So yeah, these resources can be, they're just indices, right? They can be put in buffers, they can be passed around however you like. They could be like passed around through the rasterizer state. They could be set out via the pixel and everything like this. So here I'm just reading the voxel model out from the models array here. And then here's another thing where I'm reading out, I'm just grabbing the integer for the array of, for the buffer of models. And then I am just going to index into the buffering of the first model and then get the color texture out. And I'm going to use that color texture. This should say color here, but I'm just going to sample from the color texture here, get the texel. And then, but here's another example where we can also pack extra information into like an integer, and it could have other things other than just a resource ID, right? So here is a texture and an array layer. So imagine if you have a 2D texture array that's got an array of textures, but you don't want to pass around two different variables. So you can pack into a single 32-bit integer where the first 24 bits are the actual texture array resource, and you can sort of just cast that in the shader into the resource type and then start using it. But then you can also grab the array layer that you actually want to use for this sample from the high 8 bits, and then you can use the array layer when you do your sample texture like so, and then get your texel back. So that's super handy. And also you can, because they're just indices, you can have like an enum or a constant which you just cast into a resource, which means you don't even have to pass any resources up if they're just predefined and compiled into your shaders. And you can just sample directly from the texture like so. And then also you can calculate a resource ID by taking something that's passed up from the CPU, and then on the GPU you can read it from bundle constants or a buffer or anywhere, and, or like maybe it's just computed somehow, right? And it's basically saying you can compute an offset from a base index or just mathematically compute a resource ID somehow, and then turn that into a texture and then sample from it. So we also have a maths library which bundles alongside with a compiler called hmaths. And this provides vector 2s, vector 3s, vector 4s, and matrices. And it also provides a bunch of functions that work across scalars and vector types. And it has generics, support for underscore generic, right, that we saw earlier. And it also has a few matrix functions as well. The reason why this thing exists is so we make this thing work across CPU and GPU. So it means you can just share maths functions and just use the same maths functions that you use in your game or your graphics application as you would on the GPU as well, which is super handy. So you can share a lot more code. And it doesn't actually work on the CPU just yet. So we definitely plan on getting this very soon, but it's just we've just been working on other features right now. But if you want to help in any way, please just get in contact and we can get this thing perhaps get this thing out quicker. But also we plan, when we get more of a stable footing on some of the other features, like to add more types and more functions to make this thing a lot more feature rich, a lot more useful as well. But in its current state, it's very useful already, just for GPU code, which is super nice. And also, you're not limited to using this HMaths library with the compiler. You can also use your own maths library. You just got to make sure that you use the built-in vector types for the compiler. So you can say if def HCC use these vector types. So you're not limited to using this maths library at all if it's not your sort of thing, but equally you can just plug in your own maths library and roll with that one. So there's another thing about HCC where the intrinsics are in user space, meaning that what you can do is you can just pull up a header file and just find all the built-in stuff that the compiler refers to. So this goes to things like system values and things like built-in functions. So there's no digging through some HTML page trying to find what you need, and it will be in looks kind of different from one page to another, or not quite got all the information there. But instead, it's just in some header files. You can just search through the header files, find exactly what you want in this documentation right there next to the thing. So you'll see the system values here for the compute shader. You got dispatch index, dispatch group index, and all the documentation is right here next to it. And even the built-in functions here, we've got like fwidth, which uses like DDA, DDY, and you've also got like discard pixel here, and just describes exactly how it works, what it how exactly it works under the hood, which is good. So that's super nice and very helpful as well. We also have support for shader metadata, so you can, in the HCC, specify a flag and output some metadata and compile this into your application. In future, there will be like a JSON file version, so it'll work well with like hot code reloading for your shaders. But you'll see there's an enum on the right-hand side where it lists all of the shaders that as an enum, which is super handy. So you can refer to them via some form of enumeration or ID. And then there's also all of the bundle constant structures here as well as an enum. And then you have a bunch of shader informations, which you have a string for the names of your shaders, what shader stage they are, and if it's a compute shader, what is their dispatch group size. You also have like how big the maximum bundle constants is, so that'll be really handy when you make those push constants in your in your pipeline layout, something like that. And you also have the maximum number of resource descriptors as well, so when you create your descriptor sets. And here's the bundle constant structure here as well, and you'll see there's the sort of like reflection information that's available. Right now we only give you reflection information for the actual resources, but in future we can maybe give more of a comprehensive reflection system. But for now it just tells you that, hey, there's a resource called vertices here, it's a buffer and it's read-only and it's got an offset of 16. So you can maybe do some sync code or something like this with this reflection information. So there's definitely lots of room for improvement, but right now it's definitely a helpful implementation. Although we are looking to improve this in the future and add a lot more things to it. So again, if you're interested in helping out, speeding that along, just reach out and we'll go from there. We'll also bundle a samples application. There's 6 samples. There's a basic Vertex Shader pixel shader. There's a triangle. There's a basic compute shader, so you can just copy paste these and get rolling. There's also a more complicated like ray marcher, and there's a texture sampler, so you can just see how these things are used. And there's another ray marcher here as well that is like a cube that spins out and then starts it's like an alternative color picker, which is and then there's like a voxel ray traced version of the HCC logo. It just spins around, and it's like an extruded version of the logo as voxels and just ray traced. So you can see more complicated examples and how you might use write some shader code basically. Also bundled along with the release package is a playground application. So what you can do is you just open it up. It gives you a window with your shader being rendered to the screen, and then it also gives you a little terminal window, and it gives you instructions on how to get things going. And then you open up this shader C file. You make your changes to the vertex and/or pixel shader, and you hit save, and then it recompiles it. If there's an error, it displays it in the terminal window. If there's not an error, you'll see this screen update with your latest changes. So you can have a play with the compiler, but also just like have like a offline like shader toy clone on your desktop. Right now we only support literally just running code, and there's no support for reading in textures or that are saved on the disk or anything just yet. We plan to do this in the future, but again, it's just like priorities and with other features on the compiler that we want to do first. But again, if you want to help out and add support for that, please reach out and we'll work together on that one. So we've got some links here to the actual project page up on GitHub, so you can just download it, get going today. We just did a latest 0.03 release, so we fixed some bugs, and it's all and it works on Linux and the Windows as well. There's also a Discord page, so you can come join the community where we talk a little bit more about. We can talk a little bit more about the project, ask questions, but also just join a community of C and people who program like in Vulkan and graphics APIs, things like this. We also have a Twitch where we stream the latest development. So I'm actually planning on doing a 0.1 release soonish. So working on the features like every Tuesday and Thursday at 6:30 p.m. GMT +1, and also Sunday at 4 p.m. GMT. So you can come along and see what's going on there. And there's also Twitter where I post my latest updates and just some pictures of some graphics things or little updates to the compiler. So yeah, thank you very much everyone, and have a great day.